Well, fractions are essential in the GMAT since fractions give us a chance to operate with integers. Operating numbers with just integer operations is the easiest way to handle numbers when we have to do manual calculations, okay? So let's review first the basic concept of fraction. A fraction is a number that has this form, right? It's represented as the division of two numbers called the numerator and the denominator. So whenever the numerator is greater than the denominator, well, we have a fraction equivalent to a number greater than 1. But whenever the numerator is less than the denominator, then our fraction is a number less than the unit. So it represents just a portion of the whole unit. What happens when we add fractions with the same denominator? Well, that's easy. When you, for example, sum two fractions like these, you just need to add the numerators. So you get the numerator of the sum, and the denominator will just be the same number. All right, so let's take a look at fractions with other denominators. Fractions with different denominators, we need to operate as follows. Okay, first, we need to find here the LCM. It's the least common multiple of 8 and 12. Okay, so in this case, we can try and find this number just by multiplying 12 by 2, 3 subsequently, as to see if we get a number that can be divided by 8. It happens just by chance that 12 times 2 gives you 24, and 24 is divisible by 5. So we found our least common multiple of the denominators, that would be 24, and we divide 24 by 8 first, so as to establish what is the factor by which we need to multiply the numerator 5 in order to get an equivalent fraction. So if 8 times 3 equals 24, 5 times 3 equals 15, okay? And what about the second fraction? If 24 divided by 12 is 2, that means that 12 multiplied by 2 is 24, so 7 multiplied by 2 would be 14. And that gives us a way to sum two fractions with the same denominator now. In this case, it would be 10 over 24 plus 14 over 24. And we would get the answer as 29 over 24, all right? And that would be it. Sometimes when fractions are numbers with numerators and denominators not small enough, then we can try this method. For example, let's say that you want to multiply 2 over 7 plus 1/3. So we can do special operation here. We would perform a cross product in that way, following the arms of this cross, 2 times 3. Then, since it is an addition, we say plus 7 times 1, following the other branch. And then we have the product of the two denominators, 7 times 3. That goes on the denominator. Okay? So that would be the equivalent sum of these two fractions. So we have in the numerator 6 plus 7 over 21, which gives us 13 over 21. And that would be it. Okay, so you can use the cross product approach or finding the least common multiple first, in order to convert the original terms of the sum into equivalent fractions with the same denominator. Now, what about if it is a difference, for example? Well, for differences, it's really simple. If you had, for example, 5/8 minus 7/12, you just do the same steps, but in the, middle of these two terms, we would have the subtraction sign, subtraction operator. So this would give you 1/24. Okay, so that's it. Let's talk about multiplication now. The multiplication is really simple. To multiply two fractions, you first need to simplify the numerators and denominators. That's achieved by dividing both a number in the numerators and a number in the denominators by the same factor, so that we reduce the numbers. For example, 15 and 25 can be divided both by 5. If you divide by 5, this numerator, you get 3, and here you would get a 5. So now it's like in your, you were doing this. So imagine that you are simplifying this to this actual operation. 3/12 times 32/5. It's like the original operation had been simplified to this one now. So if we proceed and repeat the same step now with two numbers, one in the numerator and another in the denominator, we would have something like this. For example, I divide 32 and I divide 12 both by 4. So if I divide by 4, I get a 4. If I divide by 4, I get a 3. Okay? So it's like now the operation had been simplified to this. 3/3 times 4/5. So you can now proceed again. Sorry, here it was 8. We divide by 4, you get 8. So here would be 8. Okay, we can still do this one more time. We can try another step. For example, now I have a 3 here in the upper part and a 3 below. So I can divide now these two 3's by 3 and I just get 1 in each case. So it's like the original operation had been simplified now to 1/1 times 8/5. So now it's clearly visible that the result would be simply multiplying the numerators and multiplying the denominators. And that would be 8/5. So the final answer would be 8/5. Okay, so that process, of course, you should keep track of mentally. Don't, this happens in your mind. Yeah, because you don't actually need to write every step. You can just do everything here, right? Simplify everything here. Let's now continue with the division of fractions. Okay, what about the division? Well, you just follow a simple rule. If you need to divide 9/8 by 5/6, then you just need to do a cross product in this way. You will multiply these two and these two numbers. The more exterior ones, you would multiply and set as the numerator. And the more interior ones, you would multiply and set as the denominator. Okay, so now you can simplify like we did before for the multiplication of fractions. You can divide by 2, you get a 3. You can divide by 2, you get a 4. Okay, so now you have 9 times 3, that gives you 27, and 4 times 5 gives you 20. So that's it. That's it. That's the result. Sometimes you could, even find the division, you know, in a linear way like this, okay? So here you can just a cross product, right? In this way, 9 times 6 divided by 8 times 5. And it gives you the same result, right? So let's continue with an example of an addition of mixed fractions. Mixed fractions are actually sums. How so? Well, it happens that, you know, 3 units and 1/2 actually means 3 plus 1/2. So if you apply the cross product rule for the sum, imagine here a denominator of 1, you can just do the cross product here, and you have 3 times 2, 6, 1 times 1, 1, and this over the product of the denominators, that means 2. So you have 7/2. So that would be the way to represent this, okay, as 7/2. What about the other? Same thing, okay? So you can just do the same here. 1 unit and 2/3 equals 1 plus 2/3, which would give you actually 3 times 2 over 3, means 5/3. Okay, so you have here 5/3. If you add these two, now you can apply again the cross product, right? Cross product here, and you have the answer. 7 times 3, 21, 2 times 5, plus 10, and divided by 2 times 3 over 6. So 31/6. Okay, that's it. So that way you operate fractions. All right, let's move on to talk about decimals. So decimals are most of the times equivalent to fractions. But operating decimals is, you know, time consuming. It can be also very tedious because you need to deal with the decimal point, which sometimes in multiplications can be harsh to deal with. So a suggestion for doing with decimals more smoothly is transforming decimals to fractions, operate all numbers as fractions, and then you can find a result, you know, using fractions. So let's evaluate how to change, you know, a fraction like this, which is a terminating decimal, right? This is a terminating decimal. That means a decimal with a given number of decimal digits. So here, how many decimal digits can you count in this fictitious number? 7 decimal digits, 3 zeros and 4 more digits. So to convert this into a fraction, just take the decimal part of the number and write it as the numerator of the equivalent fraction. In the denominator, you will write a 1, number 1, followed by as many zeros as decimal digits, as many digits you were able to count. So here we counted 7 digits. So it's a 1 followed by 7 0, which using the representation of powers, we can say this is 10 up to 7. Okay? So let's see a couple of examples. 0.312. Okay, so I just separate the decimal part, use this as a numerator, and then count the number of decimal digits. Here is 3 digits. So, because there are 3 digits, the denominator should be 10 cubed. That means 1 followed by 3 zeros. Now you can simplify this, and you will divide successively by 2, both numerator and denominator, and you get to this result, 39 over 125. Which comes, you know, after dividing each numerator and denominator by 8, okay? For example, if you have number which has an integer part and also a decimal part, then you can just split it. into the two parts. So the pure decimal, which is 0.125, you will convert into a fraction separately, and then you can put them together, because 125 over 1000 gives you 1 over 8. And if you then put together with the 3 extra units, 3 units plus 1/8 would be just, you know, the cross product is 3 times 8 plus 1 gives you 25 over 8. Okay, so that's it for transforming decimals to fractions. All right, so people, let's now continue talking about the behavior of decimals between -1 and 1. Decimals between -1 and 1, that means pure decimals actually, decimals that contain no integer part, are important because when you're given variables with exponents or roots, these numbers may have different behaviors, right? When given powers or roots. So let's talk about first the positive decimals between 0 and 1. So for this, we'll take as an example number 100 of 0.25, which is the same as 1/4, right? As a fraction. So what happens if you square 1/4? That is, you multiply 1/4 by itself, like this. So what is it? The result is you have 1 over 16, right? And 1 over 16 is a fraction smaller than the original one, than 1/4. So for this one, you actually can see that the power of a given positive decimal is always less than the original decimal. And this applies to powers of greater positive exponents, such as x cubed, and so on. What happens, on the other hand, with roots or radicals? For example, what if we took the square root of 1/4? Well, a number that multiplied by itself, you know, is 1/4 is just 1/2, right? So 1/2 is the square root of 1/4. But you can see 1/2 is greater than 1/4. So this sets the rule. Roots of positive decimals are always bigger than the original decimals. What happens with the inverse of a positive decimal? Well, inverse can be represented by, you know, the number with exponent -1. That means the inverse of a number, 1 divided by the number. So in the case of 1/4, this would be actually 1 over 1/4, which means actually 4, right? So you can see that powers with negative exponents are always greater than 1 if they are the powers with negative exponents of positive decimals, okay? Much bigger than the original numbers. Now let's talk about what happens with negative decimals. Well, negative decimals first, they have some restrictions because negative decimals, for example, -1/8. Well, first of all, when you talk about taking roots, you cannot take the square root or the 4th root, right? This thing, -1/8, or a 4th root of -1/8 don't exist, right? Because we cannot take the square root or the square root of the square root of a negative number. Yes, but we can take roots with odd indexes, like for example this or this. So these actually exist. Okay, so no problem. So let's talk about, for example, the cube root of -1/8. What number multiplied by itself 3 times gives you -1/8? Actually, -1/2. So that is the value, right, of the square root of -1/8. -1/2 is a number further to the left of -1/8, so it's less than the original decimal. So this applies to all decimals in general. The more negative the bigger the index of the radical, if it is an odd number, right? That is the cube root of -1/8 or the fifth root of -1/8, etc. They will always be less than or smaller than the original negative decimal. What happens now with the powers? What about with the powers of a negative decimal? Well, you know that if you raise -1/8, right, to the exponent 2, that is the square, well, that instantly becomes positive, okay? So in this case, probably y squared would be over here. But what happens with the odd exponents? For odd exponents, then you need to consider this. For example, -1/8 up to 3, that would be -1/512, which is a number very, very close to 0, much closer to 0 than -1/8. So if it is actually to the right of the original number, it is greater than -1/8. All right, so now let's consider what happens with the negative or the inverse of a negative decimal. So here, this would be, right, 1/-1/8. And that, of course, is -8. Remember that the inverse of a negative decimal or any number is just y up to -1. It's the same, right? So usually powers with negative exponents will be much more negative than the original negative decimal. So remember this order and the way exponents and roots for negative and positive decimals behave, okay? So let's now talk about exponent rules. Exponent rules are the rules for operating powers, okay? When you want to operate powers, what you need to do is considering that an exponent just means the number of times a factor is taken. For example, when I say x up to m, this actually means x multiplied by itself m times. Okay, so this is the meaning of a power. A power is just a product, okay, of a factor multiplied by itself a given number of times. Okay, people, so let's now proceed to the first of these properties. When you multiply two powers with the same base, you just need to add the exponents of the powers. Example, 7 up to 2 multiplied by 7 up to 10 will give you 7 up to 12 because 2 plus 10 gives 12. Okay, so this is it. Second property, when you divide a power, okay, by another power with the same base and a lesser exponent, then the quotient will be a power of the same base up to an exponent which is the difference of the two exponents. That is 5 minus 2 will be 3. So that's it. What about if you raise a power to a given exponent? Example, 5 up to 5 and this up to 7. So that would be calculated just by setting the same base and the exponent would be just the product of these two exponents. That means 5 times 7, that is 6 up to 35, okay? Well then, we already have these two properties. Now, next property is raising to a certain power a product of two factors. You can just multiply the powers of the factors with the same exponent. Example, 63 up to 7 is actually can be expressed like 9 times 7 up to 7. And of course, since this is a product, you can split this like this. 9 up to 7 times 7 up to 7. Okay? Then, what happens if you have, for example, two powers with the same base? Okay? And these two powers are equal to each other. So, it follows that the exponents of these two powers must be the same. Example, they tell you something like this, okay? Look, I have 2 up to 3x plus 2, okay? 3x plus 2. So, and I don't know, here they tell you that this number, right? 2048. Okay, you have that equation. How do you solve x? Well, it follows that you could just realize that this 2048 is 2 times 1024. Why is 1024 relevant? Well, 1024 happens to be a very well-known power of number 2. It is actually 2 up to 10. So, this means that you have on the right side of this equality 2 up to 11. So if 2 up to 3x plus 2 equals 2 up to 11, that means that 3x plus 2, the exponent on the left side, should be equal to the exponent on the second side of the equation. So if 3x plus 2 equals 11, then it follows that x must be 9, or sorry, 3. Yes, and then you solve out this variable. Okay, some of the properties regarding powers and roots are these two. Radicals. When you take the root, square root, for example, of a product, you can just split it as the square roots of the factors of this product. Okay, so for example, square root of 63 can split like square root of 9 times square root of 7, since 63 is 9 times 7. But square root of 9 is actually 3, so it could be expressed more succinctly like 3 times square root of 7. What about the root of a power? Well, the root of a power can be expressed like a power with a fractional exponent. Example, if I have the fifth root of, let's say, 7 up to 15, then this means that this is 7 up to 15 divided by 5. So this would be 7 up to 3, 7 cubed. Okay? That's a way how you can solve roots of powers. What about the negative exponent minus 1? You know, the function of this negative exponent is just inverse the base. Okay, so it's a way to represent the inverse of a number. And it doesn't actually change the sign of the original number. Okay, and x up to minus 1 or 1 over x is called the reciprocal of x, right? What happens when you have a sum or subtraction of the form x up to n plus or minus x up to n? You can only factor out the smallest of the two. Like, for example, in this case, 2 up to 9 minus 2 up to 5 equals 2 up to 5 multiplied by 2 up to 4 minus 1. Why? Because here we are just applying the distributive property, right? It's like having something like this, a times b minus a times c. So you factor, common factor here, multiplied by the difference of the other two factors. Same here, right? Because a times b, 2 up to 5 times 2 up to 4 gives you the original 2 up to 9. Okay, so let's do this, and remember that when you have this, don't ever apply this or this, because those properties are only applicable to the multiplication and the division of two numbers, okay? You cannot do anything with those properties when you have a sum or a subtraction. So talking about place values of decimals, right? Place values of decimals are very important because you have actually different positions, you know, and each digit of a real number stands for a different value. They're not just equivalent. For example, first position to the left of the decimal point is called units, but the second is called tens, hundreds, thousands, etc. To the right side of the decimal point, you have tens, hundreds, thousands, and notice the suffix THS here, ordinal numbers, so they are decimal positions. Always the decimal point is what you have to separate decimals from integers, right? The comma in the GMAT is for separating thousands or millions. And it's very important to remember the names of the place values because it's essential for rounding, okay? When you round to the nearest place value, you need to focus on the digit to the right of the digit you want to actually round. Example, if we round off this number to the nearest hundredth, first pinpoint the 100th digit. The 100th, according to this scheme, would be this, right? Second position to the right of the decimal point. So if this is it, the one we want to round, then we decide whether to keep the same digit or round it up one more unit, by checking the number to its right. Only that. The others don't matter for this. So we have 4,549.23 because 4 is less than 5. So the effect is that 3 remains the same and everything else be 0, right? Which you don't actually have to write. Just 0.23 would do it. Now, what would happen if instead of rounding to the nearest hundredth, we would round, for example, to the, let's mark it with a different color now, to the nearest thousandth. Okay, notice the TH at the end. So now we pick the position. This time would be 4, and the number we need to check. To the right of 4 would be 9. The rest we don't care, right? So here, this one commands that 4 should be upgraded 1 unit. So the rounding would become 4,549.235. Yeah, the 4 just go up 1 more, right? And the rest becomes 0, which you don't actually need to write. It's okay to write 0.235. Okay, so that's it. Let's now talk about the last concept for this lesson, which is rationalization. Rationalization is important whenever you find results with radicals in the denominator. Okay? Why is that relevant? Well, usually you may be solving a geometry problem, you find your answer, it's 2 over square root of 3, then you check the answer choices and no, not even one of them matches your answer. So, doesn't necessarily follow that you were mistaken. Might mean you just forgot to rationalize. And rationalize is a process by which you transform any fraction with a radical in the denominator into a fraction that doesn't have the radical in the denominator but in the numerator. For example, in this case, we just multiply by the same factor, the same denominator, both up and down. So by multiplying by the same factor, numerator and denominator, we're actually multiplying everything by the unit. So it doesn't change the value of the expression, but it changes its shape, because now multiplying the root by itself will give us an integer in the denominator, while this root will appear now in the numerator. So this is it, the rationalized form. This is what your actual answer choice might look like. You might have to rationalize first before you mark the correct answer choice. What about when we have an expression with a sum or a difference involving one radical in the denominator? Well, what we need to do is actually multiply by the same expression, but just with the reverse operation. Like, for example, if it is a subtraction, we would multiply by the sum of these two terms. And if it were an addition, we will multiply by the subtraction, by the difference. So here, multiplying by this and by this, both up and down, well, we get actually the same expression. We are just changing its look. How so? Well, multiplying the difference of two numbers by its sum, it's this. It gives you the difference of the squares of the two numbers. So what would be this? It would be the square of square root of 3 minus the square of square root of 2, which would give us 3 minus 2, which is actually 1, right? But in the numerator, the radicals appear again. So finally, the expression rationalized and all is this. Okay, let's do one more example. For example, I say, okay, I have 7 divided by, let's say 5 minus square root of 2. So, what is it? Well, we multiply both numerator and denominator by the sum of the actual numbers in the denominator. By multiplying by the sum, we form now this product here that equals to the difference of squares, meaning 5 squared minus 2, which is actually square root of 2 up to 2. So here we would have 7 times 5 plus square root of 2 divided by 25 minus 2. So we have the answer 7 over 23, 5 times 5 plus square root of 2. So that's it.